Every single year, humans throw away over 92 million tons of clothing and textiles, enough fabric to cover the entire state of Delaware 3 feet deep. The average person discards 70 pounds of clothing annually, with most garments being worn fewer than 10 times before ending up in landfills where they'll remain for over 200 years. But here's what most people don't realize. Nearly 95% of discarded clothing could be recycled or reused instead of rotting in dumps. So how do millions of old t-shirts, jeans, and sweaters get transformed back into valuable materials? How does a worn-out cotton shirt become insulation for your home? Or yesterday's polyester dress become tomorrow's new jacket? Today we're breaking down the incredible process inside one of the world's largest clothing recycling facilities, where over 800 tons of discarded garments get completely transformed every single day into new products that serve entirely different purposes. Make sure to subscribe as we uncover the fascinating technology and engineering behind giving old clothes extraordinary new lives. The journey begins at collection points scattered across entire metropolitan areas, where massive bins accept everything from designer dresses to worn-out work uniforms. These aren't random donations. Each piece of clothing carries potential value that trained sorters can identify and extract. Vintage band t-shirts might fetch premium prices from collectors, while high-quality wool coats could be resold directly to consumers. But the real volume comes from damaged, stained, or completely worn-out garments that most people consider worthless trash. Collection trucks equipped with hydraulic compaction systems gather tons of clothing daily from donation centers, retail drop-off points, and municipal collection programs. These specialized vehicles can compress loose clothing to 1/10 of its original volume, allowing each truck to carry up to 15 tons of textiles per load. The compression isn't random either. Pneumatic systems apply precisely controlled pressure that compacts without damaging fabrics or creating tangles that would complicate later processing. When these massive loads arrive at the recycling facility, they face immediate challenges that would overwhelm conventional sorting operations. Mixed in with legitimate clothing donations are shoes, handbags, household linens, curtains, and countless non-textile items that somehow found their way into clothing bins. The first critical step involves separating actual clothing from everything else that could damage downstream processing equipment or contaminate final recycled products. Conveyor systems, specifically designed for textile handling, move the mixed donations through initial sorting stations where trained workers remove obvious non-clothing items. These workers can process over 3,000 individual pieces per hour, their experienced eyes instantly identifying leather goods, rubber items, or synthetic materials that require different recycling approaches. Speed is absolutely critical because the facility receives over 200,000 individual garments every single day. But manual sorting represents just the beginning of a complex separation process that relies increasingly on advanced technology. Automated systems use near-infrared spectroscopy to identify different fiber types at molecular levels. Because recycling processes for cotton differ completely from those required for polyester, wool, or synthetic blends, these optical sorting systems can analyze fabric composition in milliseconds, achieving identification accuracy rates exceeding 98%. The first major separation divides clothing into natural fibers versus synthetic materials. Cotton, wool, linen, and silk require mechanical recycling processes that break down fibers physically, while polyester, nylon, and acrylic synthetics can undergo chemical recycling that returns them to their original molecular components. This separation is absolutely critical because mixing natural and synthetic fibers during recycling creates inferior products unsuitable for most applications. Color sorting represents another crucial classification step because darker colored fabrics contaminate lighter materials during processing. Advanced color detection systems use hyperspectral imaging to identify subtle color variations that human eyes might miss, separating whites from creams, distinguishing navy from black, and identifying colors that could bleed during wet processing stages. Even tiny color variations matter because recycled fibers often get used in applications where color consistency is essential. Quality assessment systems evaluate the condition of individual garments using computer vision technology that can detect holes, stains, excessive wear, and structural damage. Garments in good condition get diverted to resale channels where they can serve their original purpose for additional years. maximizing the value extracted from each piece while reducing the volume requiring actual recycling processing. This triage approach ensures that recycling capacity gets used efficiently for items that truly need reprocessing. Garments requiring recycling processing undergo detailed preparation that removes all non-fabric components that could damage equipment or contaminate final products. Automated systems detect and remove buttons, zippers, snaps, and decorative elements using magnetic separation, air classification, and mechanical picking systems. Even thread used for stitching gets removed because different thread materials could create inconsistencies in recycled fiber properties. Chemical testing analyzes fabric samples for dyes, finishes, and treatments that could interfere with recycling processes. Some clothing contains fire retardants, water-repellent coatings, or antibacterial treatments that require special handling to prevent toxic emissions during processing. Laboratory analysis can identify over 50 different chemical treatments commonly used in textile manufacturing, ensuring that incompatible materials get processed separately to maintain worker safety and environmental compliance. The prepared clothing now flows toward specialized processing lines designed for different fiber types and intended end products. Cotton recycling lines use mechanical processes that gradually break down fabric structure while preserving individual fiber integrity. Synthetic recycling systems employ chemical processes that dissolve polymer chains before reforming them into new materials, with properties often superior to the original fabrics. The mechanical recycling process for natural fibers resembles a controlled demolition of fabric structure, using specialized equipment that systematically breaks down woven and knitted textiles while preserving the integrity of individual cotton, wool, or linen fibers. Massive shredding machines equipped with precisely engineered cutting blades rotate at carefully controlled speeds to slice through fabric without damaging the underlying fibers that will become the foundation for new products. These industrial shredders operate nothing like paper shredders or wood chippers. The cutting mechanisms use counter-rotating drums with hundreds of precisely positioned blades that create specific shear patterns optimized for textile destruction. The drums rotate at exactly 400 revolutions per minute, fast enough to efficiently process tons of clothing per hour, but slow enough to prevent fiber damage that would reduce the quality of recycled materials. Cotton garments undergo a particularly fascinating transformation as they move through sequential processing stages that gradually reduce fabric structure to individual fibers. The first stage breaks garments into strips roughly 6 inches wide, while subsequent stages reduce these strips to smaller and smaller pieces until only loose fibers remain. Dust collection systems capture fiber particles throughout this process, because even the smallest cotton fragments have value in specialized applications. Temperature control during mechanical processing is absolutely critical, because friction from cutting and tearing operations generates heat that could damage natural fibers. Cooling systems maintain processing temperatures below 120 degrees Fahrenheit, well below the degradation threshold for cotton and wool fibers. Infrared monitoring systems continuously track equipment temperatures, automatically adjusting processing speeds if heat buildup threatens fiber quality. The recovered fibers undergo intensive cleaning processes that remove residual dyes, finishes, and contamination accumulated during their previous life as clothing. High-pressure washing systems use heated water and specialized detergents to strip away chemical treatments while preserving fiber structure. The washing process isn't gentle. Powerful jets blast fibers from multiple directions, while rotating drums create mechanical agitation that scrubs away stubborn contaminants. Color removal from recycled fibers requires sophisticated chemical processes that can strip dyes without damaging the underlying cotton or wool structure. Bleaching systems use carefully controlled concentrations of hydrogen peroxide or sodium hypochlorite, with pH monitoring, ensuring that chemical conditions remain within narrow ranges that remove color while preserving fiber strength. The bleaching process can take up to 6 hours for heavily dyed fabrics, with multiple rinse cycles ensuring complete chemical removal. Synthetic fiber recycling follows an entirely different pathway that breaks polymer chains back to their original molecular components before reforming them into new materials. Polyester clothing gets processed through chemical recycling systems that literally dissolve the fabric structure using specialized solvents or high-temperature processing that returns polyester to its base chemical components. This molecular-level recycling enables creation of new polyester with properties identical to virgin material. The chemical recycling process for polyester begins with intensive preparation that removes all non-polyester components, including cotton threads, buttons, and fabric blends that would contaminate the chemical reactions. Automated sorting systems achieve purity levels exceeding 99.5% because even tiny amounts of contamination could ruin entire batches of recycled polymer. This level of purity requires multiple passes through different separation technologies. Depolymerization systems heat-sorted polyester garments to temperatures exceeding 500 degrees Fahrenheit in carefully controlled atmospheric conditions that prevent unwanted side reactions. The process breaks the long polymer chains that give polyester its strength and flexibility, reducing complex fabric structures to simple chemical compounds that can be purified and reformed. Specialized reactors contain these high-temperature processes while recovering valuable chemicals for reuse. Quality control during fiber processing involves continuous testing that ensures recycled materials meet specifications for their intended applications. Fiber length measurements verify that mechanical processing preserves adequate fiber dimensions for spinning into new yarns. Strength testing subjects sample fibers to tension loads that simulate the stresses they'll experience during manufacturing of new products. Chemical analysis confirms that cleaning processes successfully removed all contaminants. The cleaned and processed fibers now undergo reformation processes that transform loose materials back into usable textile product. Carding machines align recycled cotton fibers in preparation for spinning, using rotating cylinders covered with thousands of fine wire teeth that organize fibers into continuous streams. The carding process removes any remaining short fibers that would create weak spots in new yarns, while orienting longer fibers for optimal spinning performance. Spinning systems twist aligned fibers into continuous yarns, using techniques adapted specifically for recycled materials. Recycled fibers often have different properties than virgin materials, requiring adjusted spinning tensions, twist rates, and lubricant applications to achieve acceptable yarn quality. Modern spinning equipment includes sensors that continuously monitor yarn strength and uniformity, making automatic adjustments to maintain consistent quality throughout production runs. But not all recycled clothing becomes new textile products. Significant volumes get processed into entirely different materials that take advantage of fiber properties without requiring the expense and complexity of yarn spinning. Cotton fibers become high-performance insulation materials that outperform traditional alternatives while providing superior moisture management. Wool fibers get processed into acoustic dampening materials that reduce noise in automotive and construction applications. The non-woven products manufacturing process transforms recycled fibers into sheets, bats, and formed products using techniques that bond fibers together without spinning or weaving. Needle punching systems use thousands of barbed needles to mechanically entangle fibers, creating strong sheet materials suitable for filtration, insulation, and padding applications. Chemical bonding processes use specialized adhesives to create products with specific performance characteristics. Thermal bonding represents another fascinating application for recycled synthetic fibers, where controlled heating partially melts fiber surfaces to create permanent bonds between individual filaments. This process creates products with properties impossible to achieve through traditional textile manufacturing, including materials that combine flexibility with dimensional stability, and products that resist moisture while maintaining breathability. The final manufacturing stages transform recycled fibers into finished products that often outperform their virgin material counterparts while serving entirely new purposes. Advanced weaving systems create technical fabrics from recycled polyester that exhibit superior moisture wicking, UV protection, and durability compared to traditional athletic wear. These high-performance textiles demonstrate that recycled materials aren't inferior substitutes, but can actually deliver enhanced functionality through innovative processing techniques. Quality testing of recycled textile products involves standards more rigorous than those applied to virgin materials because manufacturers must prove that recycled content doesn't compromise performance. Tensile strength testing subjects fabric samples to forces exceeding 500 pounds per square inch, verifying that recycled fibers maintain structural integrity under extreme stress. Abrasion resistance testing simulates years of normal wear through accelerated laboratory procedures that can predict product lifespan with remarkable accuracy. Color fastness testing ensures that recycled fabrics won't fade, bleed, or change appearance during normal use and cleaning cycles. Samples undergo exposure to intense ultraviolet light equivalent to months of sunlight, while washing tests subject materials to hundreds of laundry cycles using various detergents and temperatures. These tests verify that recycled textile products will maintain their appearance and performance throughout their intended service life. The environmental testing protocols examine recycled products for any chemical residues that could pose health or safety risks. Gas chromatography systems can detect volatile organic compounds at concentrations measured in parts per billion, ensuring that chemical processing hasn't introduced harmful substances. Heavy metals testing verifies that recycled materials meet safety standards for direct skin contact, particularly important for clothing and bedding applications. Specialized applications for recycled textiles continue expanding as manufacturers discover new ways to utilize the unique properties of processed fibers. Automotive manufacturers use recycled cotton and polyester for interior panels, seat padding, and sound dampening materials that reduce vehicle weight while improving passenger comfort. The aerospace industry employs recycled carbon fiber composites in non-critical applications where weight savings provide significant fuel efficiency benefits. Construction applications represent one of the fastest growing markets for recycled textile products. Recycled cotton insulation provides superior thermal performance compared to traditional fiberglass, while offering better moisture management and easier installation. Geotextile fabrics made from recycled polyester prevent soil erosion, reinforce roadway construction, and provide drainage solutions that last decades without degradation. These applications transform clothing waste into infrastructure components that serve society for generations. The medical industry has discovered remarkable applications for recycled textile materials in non-critical applications where sterility isn't required but performance matters. Recycled polyester becomes medical gowns, bed linens, and privacy curtains that offer superior comfort and durability compared to traditional materials. Wound care products utilize recycled cotton fibers that have been processed to achieve medical-grade purity and softness. Agricultural applications showcase the versatility of recycled textile materials in supporting food production while reducing environmental impact. Recycled fabric becomes crop protection, covers that shield plants from insects and weather while allowing air and moisture circulation. Erosion control blankets made from recycled fibers prevent soil loss on slopes and construction sites, gradually decomposing to enrich soil as vegetation becomes established. The facility's waste management systems ensure that virtually nothing gets discarded during the recycling process. Water used for cleaning and processing gets treated through biological systems that remove chemical contaminants before discharge. Solid waste consisting primarily of removed buttons, zippers, and non-textile materials gets sorted for metal recovery and plastic recycling, achieving overall waste diversion rates exceeding 98%. Energy recovery systems capture heat from various processing operations to reduce overall facility energy consumption. Thermal processing equipment operates heat exchangers that warm incoming air and water using waste heat from fiber drying and chemical processing operations. Combined heat and power systems generate electricity from waste gases while providing steam for various manufacturing processes, achieving energy efficiency levels that exceed most industrial facilities. Economic impact analysis reveals that textile recycling creates significantly more jobs per ton of material processed compared to traditional waste disposal. The facility directly employs over 600 workers in positions ranging from manual sorting to advanced chemical processing, while supporting thousands of additional jobs in transportation, equipment manufacturing, and downstream product manufacturing. This job creation demonstrates that environmental responsibility can align with economic development. Research and development efforts continuously explore new applications and improved processing techniques for recycled textile materials. Advanced chemical recycling processes promise to handle fabric blends that currently require separation, potentially increasing recycling rates while reducing processing complexity. Biotechnology applications investigate using recycled fibers as growth substrates for producing advanced materials through fermentation processes. The global impact of textile recycling extends far beyond individual facilities, as similar operations develop worldwide to address the massive waste streams generated by fast fashion and consumer culture. International cooperation ensures that recycling technologies and best practices spread rapidly, while standardization efforts enable recycled textile products to compete effectively with virgin materials in global markets. Innovation in product design increasingly considers end-of-life recycling requirements. with manufacturers designing clothing and textiles for easier disassembly and material recovery. This circular design approach promises to dramatically increase recycling efficiency while reducing the environmental impact of textile production and consumption. Future textile products may be designed specifically for multiple recycling cycles, extending material lifespan indefinitely. This remarkable facility processes over 290,000 tons of discarded clothing annually, diverting enough textile waste to fill a football stadium while producing recycled materials that serve countless applications from automotive components to agricultural products. The next time you donate old clothes or purchase products made from recycled materials, remember the incredible technology and human ingenuity that transforms yesterday's fashion into tomorrow's solutions. And there you have it, the absolutely fascinating process of transforming millions of pieces of old clothing into valuable new materials every single day. The innovation, environmental responsibility, and economic potential of clothing recycling demonstrates how waste can become a resource through advanced technology and creative engineering. What other recycling processes would you like us to explore? Drop a comment below and let us know what you think. And don't forget to like, share, and subscribe to keep exploring more fascinating industrial journeys with us.